Hello EMERTXE, this is Lohith recording internship report. So what are the things I learned in this 1 month of internship is how to build real-time EV dashboard and ADAS voting system. I learned how sensors, STM32 logic, UART data and dashboard communications or these four communicate each other and work together. So these are the things I learned. My learning roadmap. First I learned about the basics, GPIO, and then moved to ADC and then timers and UART. After understanding these basic faults, I moved to EV logic, which is like speed, torque, SOC and regenerative braking, and then I learned ADAS concepts like collision warning systems and blind spot detection. And then what are the applications that are used in this internships is STM32 Cube IDE, STM32 Blue Pill, and Pixel. Actually STM32 Blue Pill is in the same STM32 Cube IDE application. So STM32 Cube IDE is used to configure the microcontroller peripherals and write the firmware, and my target controller is STM32 Blue Pill, and for testing I used a Pixel lab, which helped me to simulate the STM32 board, potentiometers, ultrasonic sensors, LEDs and UART terminal without depending fully on hardware. What are the core embedded concepts I learned in this internship? First, GPIO. GPIO was used to control LED outputs for warning indication, and then ADC, which is analog to digital converter. It is used to read analog sensor values and convert it into digital values. It reads the values of potentiometers in this project. Then timers. Timers were used for fixed time task execution and ultrasonic timing, and UART was used to send the processed data from STM32 to the PC, which is a virtual output for us. Okay. Then ADC. In Pixel Lab, potentiometers were used as a simulated vehicle inputs instead of actual inputs. We don't have any actual sensors to get the real inputs of the vehicle, so we used potentiometers or as a simulated vehicle inputs. And PA0 as accelerator, and PA1 as brake, and PA2 as initial SOC, and PA3 as motor temperature. And ADC converts analog input into a digital value. Then the firmware maps ADC values into percentage, which is the ADC converts the analog signal into a digital value, and then the digital value is converted into a percentage or a temperature value. And then timers. Different timers were used for different purposes. So timer 1 is used to EV update tick for 10 milliseconds, and the timer 2 was used as a microsecond counter for ultrasonic echo measurement. Then timer 3 was used for periodically reading sensors, updating ADAS logic and checking faults. And then literally timer 1 triggers the EV controlled update, and timer 2 measures the ultrasonic echo pulses accurately, and timer 3 reads or updates and fault checks the ADAS. Okay, EV control logic I learned. What are the EV control logic I learned? So the accelerator input is converted into motor torque. When accelerator input increases, torque also increases. So then the vehicle speed also increases simultaneously. So the brake input is used for regenerative braking. When brake is applied, the torque becomes negative, which is inversely proportional to each other, brake and torque. So this represents energy recovery during braking. So I also learned about drive modes like eco, normal and sport modes. These modes change how strongly the vehicle responds to accelerator input. Then ultrasonic sensor measurement. The STM32 sends a short trigger pulse to the ultrasonic sensor. After that, the sensor sends back an echo pulse. The time duration of the echo pulse is measured using a timer. So from this echo time distance calculated, and in our project we use like 3 ultrasonic sensors, and which represents the front, left and right zones. So we use 3 timers too. Then ADAS logic. The front ultrasonic sensor is used for fault collision warning, and if the front distance becomes less than the warning limit, the system gives a collision warning. If it becomes even closer, it becomes a critical collision condition. It becomes a critical condition that we can't avoid to hit. And I learned about TTC topic, which is called time to collision. It is calculated using a distance and a vehicle speed. If TTC is low, that means the vehicle may reach the obstacle quickly. So for blind spot detection, the side sensors are used, like left and right sensors, ultrasonic sensors. So blind spot warning becomes active only when the vehicle is moving above a certain speed and an object is close to the left or right of the vehicle. And I also learned about hysteresis, which prevents warning from turning on and off the vehicle. Yeah. Then vehicle state machine. So a state machine is used to control the vehicle behavior in an organized way. So the vehicle starts in power state. When accelerator input is given, it moves to ready and then driving state. When brake is applied, it enters regenerative state, which regenerates or charges the battery in it. If a serious issue is detected, the system moves to fault state. Okay, so these are the vehicle states. Okay, then fault management. So I already told that the vehicle can move into a fault state when the fault occurs. So what is fault management? Let's manage the fault. Fault handling is important because the system should detect the unsafe conditions. So faults are checked for high motor temperature and low SOC and critical collision in our project. So when any of these conditions happen, a fault flag is set. The vehicle then enters the fault state and the warning output is activated. Okay, we can see that if the motor temperature is greater than or equal to 90 degrees Celsius, or SOC is less than or equal to 2%, and of course the critical collision, the fault occurs and the vehicle enters into the fault state and turn on PB11. Okay, then UART and dashboard integration. So after processing EB and RS values, STM32 sends the data through UART, and UART acts as the bridge between the embedded firmware and the computer. Yeah, UART acts as the bridge. Of course, it gives the output, in a virtual way that we can analyze or see visually. The data is sent in a fixed format. So one port contains EV values like speed, SOC, temperature, range, accelerated brake, and another port contains the front distance and the left and right distance, TTC, collision state, and blind spot status, of course our alarm and filter. And the Python program reads this UART data and separates each value and updates it in the dashboard. And the final learning. To conclude, the internship helped me understand how an EV engineer or EV designer designs this EV dashboard, which gets the input from the vehicle and gives a great output for the customer or a driver to know what is happening, the speed, how many kilometers, or what are the dangers surrounds the vehicles, like someone hitting the bike from the right or left, we can know it. I practiced STM32 peripherals like GPIO, ADC timers, and UART. I also learned sensors, how sensors interface using ultrasonic sensors. So on the software side, let's go. I learned EV control logic, RS warning logic, state machine logic, fault management, and dashboard communication. So the biggest learning from me is that an embedded project is not only about writing code. I really liked writing code, and then I liked and loved how the code I've written or the teacher helped me to write, but still the code I'd written gave me a great output. So this is what are all the things I learned in this internship of the duration 1 month. And thank you.
Hi Emertxe, I wanted to inform you guys that I've uploaded ultrasonic sensor assignment but it's not graded yet. I unfortunately missed the Disha workshop quiz. I kindly request you guys to open the link. Thank you so much Emertxe for this wonderful opportunity. Hello Emertxe, let's see the output of our internship. Here the acceleration is at high, brake is 0 and SOC at high and temperature at the middle. I've kept other values at high. Let's see the output. Okay, here we can see the speed increases and the torque increases because actually when acceleration is high, the torque increases with acceleration. So the speed always increases when acceleration is high. And we can see the values of forward, left and right collision the same as the input values. Okay, let's see the other output. When I increase the brake, now we can see the speed decreases as we increase the brake because the vehicle gets into the regenerative mode, so the speed decreases when torque becomes negative. Okay, let's see the collision output. Mm, decreasing the front collision value. Here we can see the indication of the critical alarm in the LED. Python dashboard, we can see it, the critical alarm and the how much distance the vehicle before us. Okay. Let's see the now I'm increasing the front. Let's see the left collision. Now we can see the LED, blue LED, which represents the left collision. Here it represents the visual representation of the left vehicle hitting our vehicle, which is a representation, and advisory alarm. The alarm shows advisory. So we can see here the speed increases because the acceleration increases and brake is 0, and SOC decreases because of the speed. When the speed increases, the battery decreases. Now see the right collision. We can see the indication of the green light, which represents the right collision of the right blind spot collision of them. And yeah, here we can see it. And this is the visual representation of the right blind spot collision. Okay, how about fault? Okay, this is the output of our internship program. Thank you so much.